It's 6 o'clock.
I think still there are almost 20 more participants, I think.
Maybe we can wait for a minute and then start.
Yeah, sure.
Is that
Okay.
okay? So 6:01 we will start.
Yeah.
So shall I start, Sushavan?
Yeah, I think we can start. Yeah.
Okay. So there are about close to 50. They will come in as I.
Yeah, sure. Yeah, we can start.
But if it is in general better to start 5 minutes later, we can do that also. Is there anything happening till 6 for many people?
I think we can start. I think slowly. I think it's increased. Number of participants are increasing. Yeah.
Sure, sure. Okay. Okay.
Good
So,
evening, sir.
hi everyone. So, like I'll continue. I mean, continue in the sense. Last time I just gave an overview of some problems in linear algebra. So today we will start with somewhat more systematic way. I mean, of course, it's not possible to cover a whole subject in this few lectures. That's not the intention either. Maybe to highlight a few things. Maybe to say things in a more disorganized way. That is, whereas books tell you in an organized way. So the way different ways, and then you get better understanding. So let's go over some of the things. So I will start with some abstraction. So vector spaces. So what are vector spaces? Okay, so vector space V. So you all know the definition. I'm not even going to write a definition. So it is a set with two operations, right? So here we will only consider vector spaces over real or complex numbers. Okay, so these are real numbers or complex numbers. So some of you, or maybe all of you, are familiar that perhaps know that vector spaces can be defined over general fields. But just to keep things simple, we will try to we'll stay with real and complex numbers. I think Venkatesh is also going to do the same. So you can one can do a lot. Actually, there is much use in doing vector spaces over general fields, but it's okay. One can learn a lot with this, and then it's not so hard to extend that. Okay, so that's one of the things. At least different people prefer differently. Some people like to start with generalities, as general as possible. For someone like me, it is always better to start with some cases, and then once I understand the basics here, then I find it easier to go to more general situations rather than do the general one directly. So what is it? So there are two operations. As I said, I'm not going to write the full definitions. There are two operations here. One is a vector addition. And another is scalar. Okay, I'll just write dot, but we rarely even write dot, which is scalar multiplication of vectors. So the elements of V are vectors. The elements of V are called vectors, and these are scalars. The elements of these V are vectors. The elements of this are scalars. It's either real or complex numbers. And we can do two things. We can add vectors. We can also multiply scalar, any vector by a scalar. So you can, if V is a vector, you can do 2 times V. And then there are a bunch of compatibility conditions. Okay, I say compatibility, all sorts of things, associativity of addition, commutativity of addition, then distributivity of scalar multiplication over addition, all sorts of things. So I'm not even going to write them. So you will have seen them in books. So let's leave that. So that is what a vector space is. Okay, so vector space is a mathematical structure like many other structures. So this is a math structure. In mathematical structure. So we say mathematical structure. Like, if you ask me what is a mathematical structure, I won't be able to say it, but you can understand it with many examples. For example, groups. The definition of group, that gives you a mathematical structure. Groups, like groups, or rings, fields, metric spaces, topological spaces. There are any number of mathematical structures. The simplest maybe sets even, but let's say groups, rings, fields, all these are mathematical structures. Like that, vector space is a mathematical structure, and it is one of the simplest ones and very important. Okay, rather than say in abstract, so let's maybe give some examples, or maybe I add a structure, or yeah, let me give some examples rather. First, let's start with some examples. Actually, prime examples are Rn is a vector space over of tuples of numbers, which usually I will write as column vectors. You can write them as row vectors or column vectors, but just for consistency, it is this. And how do you add V1 up to Vn? You can add two of those. V1 multiplied by some scalars. Alpha, beta, I'll always use for scalars. So the definition will be that this is alpha V1 plus beta W1 and so on up to alpha Vn plus beta W. So this is the way this vector space is defined. So this here is the addition is just coordinate wise addition, and scalar multiplication also. Scalar multiplies all the coordinates. That's what it is. Similarly, Cn is a vector space over you can also make it a vector space over R. It's a bit more natural to make it vector space over C, but also Cn can also be thought of as a vector space over R. That's also fine. Then what other examples can we say? Any other examples, you know?
Polynomial.
Okay. Space of all polynomials with real coefficients, let us say.
Matrices.
Okay.
Square matrices, set of all square matrices, and n by n square matrices.
Okay, I will write that too. Let me first finish this one. Space of all polynomials with real coefficients. They are objects like this. Polynomials can be just written as tuples, but it is usual to write it like a0 plus a1x plus anx to the n. X is a meaningless symbol here. Don't have to think of it as it's just a variable. It doesn't mean anything. If you want, you can write it as a0 up to n, where n is any n is greater than or equal to 0, and ai's are real numbers. So this is the space of all polynomials. So we can call it P sub R. You can do the same with ai's in complex numbers, then they become complex polynomials. So this is a vector space over R. Okay. And so somebody said n cross n matrices. Mn cross n is the set of all Aij are in R real numbers. So this would be Mn of R. Mn cross n of R. Similarly, you can define over complexes, etc. What else? So
Trace of a matrix.
huh?
Trace of a matrix.
Trace of a matrix is not a vector space.
Set of all symmetric matrices.
Set of all symmetric matrices, we can take that. So we can take Sn to be the set of all A in Mn of R such that A transpose is equal to A. Okay, so that is a subset of this. So as we will see, this is a what is called a subspace of that, but we will come to that. Okay, so if you take the space of all symmetric, so these are symmetric matrices. So this is also a vector space. So there are many vector spaces. Let me give a slightly different kind of example, or not really very different, but something else also to keep in mind. You can look at C01.
Set of all convergent sequences.
1 second, I'll come to that.
Set of all bounded functions on closed interval AB.
Okay, let's see if that is a vector space. So let's look at f of from 01 to R such that f is continuous. Okay, f from 0 to R, 01 to R, f is continuous. This is a vector space. What does it mean to say? What is the operation? I didn't tell that. You can add functions by adding them pointwise, and you can multiply. 2f means the function which gives the value 2 times f of x to x. So you suggested a different one. Let's call. If you take all functions from 01 to R, that is also a vector space. But you had a different condition, f is bounded. Okay, that's also a vector. Is it a vector space or not?
Yes, sir. It is a vector space.
It's a vector space. What about, let's take C plus of 01, the set of all functions from 01 to R plus means 0 infinity, positive functions.
No.
This is not a vector space. Why not?
Because over
Not closed scalar multiplication.
So minus f will not be there. If f is there, so this is not going to work. So this is not true. Okay, so that's not an example, not a vector space. So there are vector spaces, there are not vector spaces. I mean, lots of things you can write that are not vector spaces. So another useful kind of example always to keep in mind is another one, which I'll just put down here. L1 and L2. So let me give that. So L1 is the set of all sequences X. Elements of L1 are sequences of real numbers. Such that summation mod xi is finite. All those sequences for which the absolute value sum is finite. So this is a vector space actually, because if you add 2 sequences, how do you add 2 sequences?
component wise.
Yeah,
Element.
exactly. No, there is no limit. Just
Element
add,
wise.
huh?
We will add two vectors as element wise.
Element wise. Sorry, you said element wise. Yeah, addition is element wise or coordinate wise.
Yes.
Term wise.
So another example, L2 is the set of all sequences such that xi is in R and summation xi square is finite. This is also the same. Addition is element wise. If you add two such sequences, can you show? So maybe this is an exercise. Show that these are vector spaces. The first one is easy. Second one is also not difficult, but you need to do something at least to show it. Okay, so show that these are actually vector spaces. So we have lots of vector spaces. Another kind of thing, which is how these things were born at first, what is the following. So suppose I say it's defined in a different way.
Sir,
Yes.
is L2 a subspace of L1 or not?
Yeah, it's a good question. Is it? Is it not?
I guess it is L2 is subspace of L1.
Okay. Anyone else? Is one contained in another?
Yes, L2 sequence is always contain L1 sequence because we are taking a squares.
Squares. So which is easier to converge? If you sum the squares or if you sum the absolute values?
Sir, square.
So which is subset of which?
L1.
No, L2 is subset of L1. L1 is a bigger space than L2.
Yeah, which is easier? Which is easier to converge? Summation xi or summation xi square?
Summation xi square, sir, maybe.
So if this is easier to converge, then which is larger? Then L2
L1
is larger, right? So here is an example. Look at 1 by square root of n. What is that?
Divergent.
This is, sorry, I should not have taken 1 by square root of n. Let's take summation 1 by n. What is it? Does it converge?
Yes,
Yes?
it's not converged.
It does not converge. So this is infinity. If you do summation 1 by n square,
It's converge.
It's convergent.
so the sequence 1 to L2, it does not belong to L1.
L2, yes.
So L2 is not a subset of L1, it's the other way. If something has this is finite, then this also will be finite. You can think why.
Yes.
Okay. So now let me give a slightly different kind of example. The set of solutions to the ODE. So I write down an ODE, A of t, x dot of t plus b of t, x dot of t plus c of t, x of t equal to 0. So here derivative means okay, so x is a function. So this is a second order differential equation that I have written. So look at the set of solutions to this. So what I mean, what is a solution? So if u of t and v of t are solutions, then let's say w is 2u plus 3v, 2u minus 3v, let's say. Is that a solution?
Yes, yes, by principle of superposition.
Okay.
Any linear problem
yeah.
always has a solution.
Superposition is another name for linearity. So what you are saying is that if I write down what is u is a solution, it just means a of t times u dot of t plus, okay, if we write this, w dot will be 2 times u dot minus 3 times v dot, right? And w dot will be, because of derivatives, 2 times u dot minus 3 times v dot. It's just the first and second derivatives. Now you multiply this by c of t, this by b of t, this by a of t, and add up. Then you see that this part will cancel and this part will cancel. Then, so this is also a solution. So in general, I just wrote 2 and 3, but you can see that for any scalar multiples, So the set of solutions to this ODE, this forms a vector space, right?
Only homogeneous problem.
Well, I'll come to that, but this is a vector space. Sorry. So also 2 times u, I mean, it will be fine, right? So, okay, now let me write what you said. So if I write the set of solutions to
Linear homogeneous equation.
yeah. So the set of solutions to a of t x dot dot of t plus b of t x dot of t plus c of t x of t, let's say equal to 1. Then it is not a vector space. Because if u and v are solutions and I add u and v, then the right side will become 2. Okay. So this is not going to be a vector space. It's not a vector space. So this is not an example. This is not an example. So there are examples, there are non-examples.
Yes.
So some solutions to certain types of equations will form a vector space. That is what is called linearity. This is how linearity was born. So many things, equations in physics, some equations are linear, some are not linear. Linear means superpositions of solutions. If you have 2 solutions, you add them, you get a solution. If you have a solution, you multiply it by 2, you get another solution, etc. That is called a linearity. So there is a famous saying that the great discovery of 19th century was that nature is linear, and the great discovery of 20th century is that nature is not linear.
Sir, but this non-homogeneous problem, if u and v are the solution for this non-homogeneous problem, then u plus v by 2 can be the solution for this non-homogeneous problem. U plus
Right?
v by 2.
That's not a
Any
u plus v by 2 is, but it doesn't. U plus v by 2 is, but 2u is not. So it's not a vector space.
Yeah, yes, sir. It's not a vector space, but u plus v by 2 can be the solution of this non-homogeneous problem.
It is a solution, but why? But it is not. All I am saying is there anything wrong in this, that it's not a vector space?
Yes, sir. It's true, because general linear combination does not belongs to this solution.
Okay. So it is not a vector. That's all I want to say now. Yeah, it's not a vector space. That's all.
0 is not there. That's why it is not a vector space.
Sure. So, I mean, 0 comes after, but if you want to understand it in a somewhat abstract way, so 0 comes after you define what it is. I mean, so what you call 0 need not be the 0. Maybe there is a vector space and it has an identity which can be called 0. Okay. So, to say that 0 is not there, what is 0, first of all? So after you have a vector space, then there is an additive identity which is called 0. So the first, so yeah, that's a small point I would like to emphasize, that so 0 is not whatever you want it to be, but if there is an additive identity, it would be called 0. In this case, it doesn't even have a vector space structure anyway. Okay, so these are many examples. So what you study in linear algebra is basically, this is a study of this vector space structure. But there is so much you can do with vector space structure. So what do you do? Once you have a mathematical structure, you study, one of the main things is mappings between these structures. So I will talk more about them later, but today I will right away mention that as soon as you have a mathematical structure like a vector space, it is always useful to study objects, mappings between such objects which preserve the structure, mathematical structure. Okay. Whenever you have so let me write that in some generality. When you have a mathematical structure, It is useful. In fact, you can say it's important, or you can say it is unavoidable. To study mappings between them that preserve this structure. So when we are talking about vector spaces, what is it? We are talking about if you have V and W. Both are vector spaces, either over real or complex. From now on, I will not say at any context I may be dealing with complex vector space or real vector space, okay? But fix the field. It's not like V is over real and W is over complex and like that. It will be one field which is fixed, either real or complex, and you take a vector space over two vector spaces over that. Then what is it that we would like to study? What does it mean in vector spaces? What does it mean to study maps that preserve the structure? It means T from V to W such that, what does it mean to preserve the structure? What is the structure? The structure is vector addition and scalar multiplication. So it should be preserved. So T of U1 plus U2 should be T of U1, which is an element here, and plus T of U2. And T of alpha U is alpha times T of U. Okay, one should be very careful in the beginning when you're first time exposed to abstract structures. You have to be very cautious what all this means. On the left side, this addition is the addition on vector space V. Here, alpha U is the scalar multiplication in the vector space V. On the right side, this plus is a T of U1, T of U2 are elements of W. This is a vector T of U. T of U is an element of W. This is a scalar multiplication of a vector in W. Although we use the same plus and same dot, or I don't even write the dot, at first you should be cautious, but it is useless to introduce separate notations so that if we do that, we will just get confused ourselves. But you should realize that at first, that's what this is saying. So if you add two vectors in V and then map it, it should be same as mapping them and then adding them. Or if you do scalar multiplication and then take under the mapping, it is the same as map it first and then do the scalar multiplication. So these two can be combined in one line if you like, as T of alpha U1 plus beta U2. It should be alpha times T of U1 plus beta times T of U2. Instead of writing two lines, you can write this, but this should hold for all U1 and U2 in the vector space V and for all alpha and beta scalar. I'll just write scalar, which means it's either reals or complexes. So what are these called? What are such maps called? What are linear transformations?
Linear transformations.
So linear transformations. So that is the name given to the maps between the mathematical structure of vector spaces, which preserve the structure of the vector space, namely addition and scalar multiplication is preserved. So just to make it clear, so you can have such maps whenever you have a mathematical structure, you have such things. When you are talking about groups, what are the maps between groups that you consider which preserve the structure? It's just a different name. Somehow historically different names were given, but they are exactly the same. Mappings between groups which preserve the structure are called homomorphisms. When you are talking about, let us say, metric spaces or topological spaces, these things are called homeomorphisms. There, the structure is of open sets, and homeomorphisms are continuous functions whose inverse is continuous. I mean, Well, okay, it depends on how you define, but I just let me write homeomorphisms. It's a slight inaccuracy, but okay, it's a homeomorphism into that. So like that, whenever you have structures, you have to study. So that's why you see when you study groups, a lot of time is spent on studying homomorphisms. When you study metric spaces, topological spaces, you have to study homeomorphisms. Whenever you have a mathematical structure, you have to study mappings between them. And in case of vector spaces, those are linear transformations. Of particular importance, are maps that are bijective, and the inverse also preserves the structure. Well, I'll write it in brackets because in case of vector spaces, that is automatic. But what does this mean? So in other words, a transformation, if I have T from V to W, a linear transformation, that is also a bijection. Such a thing, what is it called?
Homeomorphism.
No,
Homeomorphism.
no,
Isomorphism.
it's called an isomorphism. Isomorphism is a very general term. What it really means is that V and W are basically the same thing. It just means okay. So it is important to understand isomorphism. Just that somehow different. So when you have a linear isomorphism, that's also a bijection. What it really means, what is the point of this isomorphism? It just means that whatever you do in V, you can do in W. If you do some calculations in V, you can immediately transfer the calculations to W and vice versa. That's what it means. So an example is, if you look at the complex numbers as a vector space over R is isomorphic to the vector space R2 over R. Here you may write things as A plus IB. Complex numbers are like this. Here you will write them as tuples. But that's just, as you can see, it is just a way of writing. There is nothing into it, right? I mean, how does it matter? When I add, I will add separately the real parts and imaginary parts. Here I will add the coordinates separately. It is very clear what the isomorphism between these two is. I will leave it for you to write down, but that's an isomorphism. So whenever you study vector spaces, you have to study linear transformations. And in particular, you should study isomorphism. When two vector spaces are isomorphic, it means they are basically the same vector space with a different kind of naming. You may call them V1, V2, Vn, and W1, W2, Wn, etc. here, but that's all. Up to label, up to names, they are the same thing. That's all. Okay, so that is what vector spaces are. But there are sometimes more structure to a vector space than just a vector space. May have more structure. There is only one that I will study, which is an inner product. Okay, so what is an inner product? So let V be a vector space. over reals or complexes is what I mean. Okay. So an inner product you would have seen is a binary operator, is a map which is usually written like this. It's a mapping from V cross V to V, such that what are the properties here? So here I just write star and star to mean that you put any two arguments from this vector space.
Sir,
So
whether
what
it is V cross V to that F, your field V cross V to F.
Well, oh, sorry. I mean, it's not to be, sorry, to scalars, which is in this case R or C. Okay, thank you. So that's a correction. So it is a mapping. You take two vectors and gives you a number, a scalar. It should have the following properties. UV should be equal to, it is almost symmetric, but if you are using complex numbers, you should write this. It's called conjugate symmetry. Or Hermitian. Property 2 is that it is linear in the first coordinate. This alpha times U1V plus beta times U2V. Okay. And third is that if you take inner product of any vector with itself, you should get a non-negative number and it should be strictly positive unless U is 0. Negative, and it is 0 only if U is 0, otherwise it can't be 0. So this is called positive definiteness. So this is linear. Of course, what this implies is also it is conjugate linear in the second variable. Okay, it's a conjugate linear. So inner product is an extra structure which a vector space may or may not have. Okay, if it is there, that is a more structure. An inner product space is a kind of richer structure, more restrictive, and hence a richer structure than just a vector space. So just going over these examples, is Rn, can you put a inner product on this? Is there any inner product here on Rn? Let's just quickly go over some of these examples.
Dot.
So in red, I will write, for example, we can take the inner product of V and U as summation Vi Wi. I equals 1 to n, what you call the dot product. So V1 W1 plus V2 W2 plus Vn Wn, that has all these properties. It has the symmetry. Because we are working over reals, there is no conjugation required. Its linearity is there in both first and second argument. And if you take inner product of V with itself, you get V1 square plus V2 square plus Vn square, which is strictly positive unless all the Vi's are 0. On complex numbers, what is the inner product? I mean, is there any inner product?
Vi Wi bar.
Yeah, in this case, you have to take the conjugate. Otherwise, you would not get an inner product, because when you interchange W and V, you should get the conjugate of this. So on polynomials with real coefficients. So when I say that there is an inner product, it means that you can put this inner product if you want. So there are two different things. If you just study Rn as a vector space, it has some structure. If you also put this inner product on it, you have a richer structure. So that's the inner product space. It's not saying that Rn as a vector space is necessarily, you should put an inner product. That's not necessarily the it's similar for polynomials. Is there any natural inner product? So there is no natural inner product there. I mean, you can put inner products. There exist inner products, but there is no natural one. On n-cross-n matrices?
Trace of A transpose B.
Okay. So
Inner product of AB is trace of A transpose B.
trace of
A transpose B.
A transpose times B. Okay. So this is an exercise. If you don't already know that, show that this is an inner product on this vector space. On C01, is there any natural inner product?
Integral
0 to 1, f and g.
Yes, sir.
F plus g of x dx.
Yeah, this would be a natural, this is one inner product. I'm not saying that you have to take it, but this is an inner product on C01. Sometimes you may want to study C01 with this inner product. Sometimes you may not want to put this inner product there. Okay. So various things like this. So L1 doesn't have an inner product. There is no natural inner product. Here there is an inner product, which is just the natural extension xi yi. Okay, the inner product of two sequences is summation. You cannot do that on L1 because this will not converge, but here this will actually converge. If summation xi square is finite and summation yi square is finite, then this series converges. Why is that?
Cauchy-Schwarz inequality.
That is from the Cauchy-Schwarz inequality. So it's not obvious. If you don't know it, then you have to think about it. From the Cauchy-Schwarz inequality, one can show that this series is convergent and meaningful and gives an inner product on L2. L1 does not have an inner product. So some vector spaces have inner product, some don't have. And inner product space is a much richer structure. So since we didn't do anything of real content, let me just take a nice fun detour here. So what are all the possible inner products? On R2. So R2 is, let me now, violating my own convention, let me write it as row vectors for just simplicity. So R2 is x comma y, x, y are real numbers. So what are all the possible inner products that one can define? So we gave one inner product, namely this one, VW is V1 W1 plus V2 W2. But are there any other inner products? Do you know any other inner product? So one is this is okay. Any other?
X transpose AY.
Huh?
X transpose AY, where
Okay,
X and Y
so-
are column matrix.
Okay. Let me just say 2W1 V1 plus 3 V2 W2. This is an inner product. You can check that it has all the properties. Okay. So I will come to what you said. So what are all the possible inner products? So for that, it is one why I am going through this is this illustrates one of the nice things about vector spaces. So you can write every vector. So if I want, if V is V1, V2, we can write it as V1 times E1 plus V2 times E2, right? So E1 is the coordinate vector 1, 0, and E2 is the coordinate vector 0, 1. And similarly, W, which is W1, W2 is W1 E1 plus W2 E2. So now what will be the vector inner product of V1, inner product of V and W. Because of, so it is so we can write it like this. Now, because of all the properties that we said here, because of linearity and so on, you can check that it is same as V1 W1 times E1 inner product E1 plus V2 W2 times, sorry. You just expand it using the linearity in the, and this one, linearity, right? So V2 W2 times E2 inner product with itself plus V1 W2 inner product of E1 with E2 and V2 W1 inner product of E2 with E1. So we get these things. So in other words, what it is telling you is that it's enough to know the inner product between these vectors alone. So if you just look at the inner product between E1 with itself, E2 with itself, E1 with E2, and E2 with E1. That's all you need to know. Then you can find the inner product between any two vectors. So that's all you need to know. So let's give them some names. If you call them, so let's give these names. Let's call them A11, A22, A12, A21. They are just numbers, okay? They are real numbers. So what are the, but is that enough? I mean, can I take any A11, A22, A12, A21? Aij are real numbers.
You should take A11, A22 should be positive.
A11, A22 should be positive. Why should A11 be positive? For example, if we take E1 inner product E1 itself, then V1 is 1, V2 is 0. So all this and W, I mean, so let's take E1 inner product E1. That has to be, directly E1 inner product E1 has to be non-negative, right? This is clear, it has to be non-negative. So these two are there. Any other conditions? So one more condition comes from here. Okay, so
E1, E2 should be equal to E2, E1, inner product of E2, E1. Because we are dealing with R.
Equal to A21. So one other thing is that A12 should be equal to A21. Because E1 inner product E2 should be E2 inner product E1. Okay, what else? You were telling something. So somebody was saying.
Coefficient matrix positive definite.
Yeah, okay. I am leading to that. The point is not the answer, but what else does it take just from the definition of inner product to get there? So the point is, like you said, there is one more condition. So one more condition.
A11 and A22 should be strictly positive.
So yeah, so what we need, what is the condition? So we need the condition is that V inner product V is positive. What does this mean? It just means that if you look at this expression, it is the same as sorry. So this whole expression, what I am trying to say is that this entire expression is nothing but you can write it in matrix multiplication form as V1 W1 A11 A12 A2 sorry V1 V2 A11 A12 A21 A22 times W1 W2. So when you put V and W to be the same, what you get here is that they are actually, this side is also V1 and V2. So you get that this is V1 and V2 should be greater than equal to 0 for all V1, V2 in real numbers with strict positivity unless V1 and V2 are both equal to 0. Okay. So this, in other words, is so already the condition that it has to be symmetric. So you see, this is this matrix. So it leads us to a nice concept of some importance, considerable importance actually. So this matrix A must be symmetric and positive definite. Symmetric is the condition that A12 is A21. And positive definite is the condition, usually positive definite also assumes symmetry, but it is this condition that X transpose AX is greater than or equal to 0 for all X with strict positivity unless X is 0. So that is what is called positive definiteness. It is a very important concept. So this naturally asking, so but this didn't reduce the problem much. We were asking what are all possible inner products. Inner products are defined by some properties, abstract properties. That has been now reduced to a somewhat reduced, but not entirely, to saying that, oh, you just need to find a 2 by 2 matrix, but satisfying this condition. It's still hard to check this condition. It will later turn out, you will see that A is positive definite. One can write it in many ways. Because why I say this is not something easy to check, right? You have to plug in all V1, V2 and check it. That is too painful. We can't do that. What we can do is A11 positive, A22 positive, and A11, A22 minus A12 square positive. So these three conditions alone are sufficient. They are the same as A is positive. So, and similar thing in higher dimension. So I don't know how much time I will get to spend on positive definite matrices. I thought I'll just introduce it here. Just as so positive definite matrices are very natural, because if you ask what are all the possible inner products on Rn, you will get any inner product on Rn. So I'm just saying that any inner product on Rn is of the form V inner product W is V transpose A W for a positive definite matrix. Now, what is positive definite matrix? Basically, that V transpose AB is non-negative for all V, and it's strictly positive unless V is 0. But in fact, one can find easier to work with conditions or in terms of eigenvalues. We will see later that it is also in terms of, hold on, eigenvalues are positive.
Sir, there is a need of A22 to be positive, but like A11 is positive definite, it's sufficient. Only A11 is positive and determinant A1.
But what will imply that? You don't have to. What you are saying is you don't need to check this, because these two conditions imply this. Yes, that is correct. If A11 is positive and A11, A22 minus A12 square is positive, then A22 must necessarily be positive.
Sir, for inner product, do we need only positive definiteness is enough, or symmetriness also needed?
Symmetry, yeah. Symmetric and positive definite, I mean, yeah. Well, if it is not, you can always reduce it to symmetric. That is the more correct statement, but let me leave it at that. Okay, I went into some slight digression, but not a digression. I mean, it's something that I wanted to tell anyway. But now let's come back to what you do with vector spaces. So one of the first things you study about vector spaces, I went into, so we'll come back a little bit to linear transformations. They are next class also I'm going to do that, but which is on Thursday. But what about vector spaces? What are the things we study? So it turns out every vectors in vector spaces, there is the notion of a basis, which is a very important thing. Basis. It is a subset of vectors that is linearly independent and spanning. So linearly independent means that, so let's say a subset of vectors. I'm writing, okay, in general, it need not be a finite set, okay? So in general, it need not be a finite set, but okay, I don't think I need to recall the definition of linearly independent or spanning. Spanning means that every vector can be written as a linear combination of. So I don't think I should, this I assume that you know the terms. Spanning means every vector in the vector space can be written as a linear combination of these vectors. And linearly independent means that no linear combination of this is zero unless the coefficients are themselves zero. So that is a spanning. More vectors you have, the easier for it to be spanning. But linear independence will be destroyed. So the point is to have both. So what this will mean that every vector can be written in as a unique linear combination of the basis vectors. Okay. So when you are studying inner product spaces, inner product spaces. When you study inner product spaces, what do you ask for? It's not enough to have basis. Okay, one of the first theorems is that you study, it is there in all books, is that every vector space has a basis. And all bases have the same cardinality. So that will be called dimension, right? That's what the dimension of a vector space is. Every vector space has a basis and all bases have this. I'm not going to go over the proof of this kind of statement. It is there in most books. You can look at it, but this is the most fundamental first theorem that you prove in vector spaces. But when you go to inner product spaces, that's not enough. What do you ask for?
Orthonormal basis.
Yeah, so you want something that goes well with the inner product structure. So when you ask for inner product spaces, you ask for orthonormal basis. So it is a basis in which any two distinct elements are orthogonal. So that is, orthogonal means inner product is zero. Two vectors are orthogonal if the inner product is zero. And again, the theorem says that they exist.
It's 7 o'clock.
Okay, I will stop in a minute. Sorry. Every inner product space has an orthonormal basis. O and B means orthonormal basis. How do you know that? I mean, so maybe that is a good thing to ask. So suppose you assume the first theorem. How do you get this theorem from the first theorem? Let's work with finite dimensional vector spaces even. Okay.
Gram-Smith orthogonalization process.
Okay. Very good. So that is something. So I'm just so as you can see, part of these lectures are just touching on various keywords and drawing lines between them. So you can go from basis to orthonormal basis by what is called Gram-Schmidt. So if you can find a basis which is not an orthonormal basis, then you can find an orthonormal basis to get it. So let me give an exercise which is worthwhile doing. Consider the polynomials with inner product you use this inner product. Okay. Apply, sorry, maybe I will do it on -1. Apply Gram-Schmidt to so 1x, x square, etc. is a basis here. Okay. So what do you get here? So you won't be able to find all of them. Find the first few, is what I mean. Find the first few. You apply Gram-Schmidt to this. It's a good exercise to learn what Gram-Schmidt is actually doing. Okay. So how do you convert? This is not orthonormal basis, you will find. But suppose you try to apply Gram-Schmidt, what do you get? When I say find first few, maybe 4 or 5 of them. Okay. Okay, I will stop here. Sorry for going a bit over time. If there are any questions, I can answer.
So can we define inner product on a
So if you
general
want to relax. Yeah.
Yeah, I think one.
Yeah.
Yeah.
Can we?
Yes.
Can we define inner product over a vector space defined over a general field, not
No,
R or C?
So the thing is, there is no question of positivity. Positivity makes sense only in real and complex fields. So that's why it is it is not a purely algebraic concept in that sense. It's not over general fields, but you can study quadratic forms in general fields. With general fields, if you remove this thing, positivity condition, then those things are important. They are called bilinear forms, quadratic forms, whatever, bilinear forms. They are important, but positivity makes sense only in real and complex scalars.
Okay. Okay. Thank you, sir.
Sure. So in the next lecture, I will just go on a little bit over linear transformations and so on. In the meantime, if people have something that they are really confused about, you can write. I'm not sure whether we can attend to all the things, but if you...
Just a second. Sir, it's a change of basis, sir. Sir, change of basis is the thing if you can.
So about change of basis. Okay, we will probably touch on that, I think. Not maybe too much, but the thing is, vector space has a basis, but there is not necessarily a natural basis, which makes a big difference. For example, for the set of real polynomials, a natural basis may look like 1x x square. But if you have the inner product, then that's no longer a natural basis. So vector space comes with, it has lots of bases, but there may be no natural one. That makes a big difference. choosing a basis is a big thing. Okay, if I am working with one basis and you are working with another basis, it is kind of a pain to convert my results to your results. That's what change of basis is about. Maybe we will touch on it a little bit next time. Okay.
Sir, in case of orthonormality, the inner product VV is 1, I think.
Orthonormal basis. Oh, yeah. Sorry, I didn't say that. You're right. Thank you. So I forgot to write that condition here. When I say they are not orthogonal, and also they have to be normalized so that they have unit norm. Thank you. Orthonormal basis means that the individual vectors should have unit norm. Not only that. Thanks. Okay, so if there are no other questions, etc., I'll stop sharing. So Kaushik will start in a few minutes. Kaushik has joined, I think. You can make him host.
Yes, I have made him a co-host. Yeah. Good evening, Kaushik. Yeah.
So Sushobhan, have you enabled sharing screen?
Yes, I have done. Are you able to share?
No, it says host disable participants
Let me
screen
just
share.
try one more time.
He's not co-host yet. As well.
Can you try now?
Okay, So then I guess you'll have to stop sharing the.
Oh, okay, yeah, sure. Is it working now?
Yeah, hang on 1 second.
Okay.
Okay. You can see my screen, right?
Not yet. I'm not able to. Can someone else confirm?
No, I also am not. It's still coming, it looks like. It's not showing.
Yeah.
It looks like it's started screening. That's it.
Maybe you can stop sharing and then start one more time. I think it will. It will.
Did you share screen or a particular application, Kosuhik?
Sorry?
Did you share screen or did you share a particular window? Ah, now it's showing.
Okay.
Yeah, now we can see.
Okay. Let me know when I can start.
I think we could. We can start. We have all the participants, and yeah, it's time. It's 7:10. We can start, I guess.
Okay. All right. So yeah, welcome to the second lecture. So today, this is the plan that I will cover sequences, mostly convergent and divergent sequences, Bolzano, Weierstrass, and so on. I mean, so I'm sure some of you or most of you would have seen many of these things, but I just want to emphasize some connections to what we did yesterday. So meanwhile, just let me remind basically the most important things from yesterday, where this property, this order completeness of real numbers, which says that, so this red box that I have done. So order completeness means that for any non-empty and bounded above set, supremum of that set exists as a real number. So this is the completeness of R. And we saw yesterday that from this, several important things follow. For instance, the Archimedean properties, right? Archimedean property, particular that if epsilon is positive, then there is an n such that 1 by n less than epsilon. This is a consequence of order completeness. Moreover, this very important theorem, which generalizes to metric spaces in terms of compact sets and so on, this is the nested interval theorem. So if you have a sequence of decreasing closed intervals, then their intersection is non-empty. This also follows from order completeness, in particular if the diameter of these intervals, if they approach 0. So this was the corollary. In particular, if bn minus an, if that goes to 0, then there is exactly 1 point in the intersection. So we did this and so on, and finally we ended with someone asked a question about is there some other ordered set with this property of completeness. So we saw that there is not a totally ordered set, but if you relax it a bit in the set partial order, then there is, right? So if you look at all subsets of some, let's say, natural numbers, then there is a partial order. It's not a total order because I've written two sets which are not comparable. But if in this one, except for the ordered part, then it's kind of satisfies this thing, barring total order. Okay, so we will continue this theme of why this completeness property of order completeness is one of the crucial things which handles almost every other result, let's say. Okay, so yeah, as with the other lecture, if you have some questions, you should feel free to ask. I don't particularly check this chat box, so it would be better if you unmute yourself and ask. Yeah. Okay, so we start today with sequences. Okay, so as I mentioned yesterday, analysis is the more or less the study of limits, okay, in various cases and so on. But so let me just recall the definition of convergent sequence. So recall, But okay, first of all, what is a sequence? Just to clarify, what is a sequence? So let's say what is a real sequence? Sequence in you can talk about sequences in various sets, but what is a real sequence? It's simply a function from the natural numbers to R. Okay, so we have something like x of 1 is a real number, x of 2, and so on. So we denote all of these are in R. Okay, so this is just a sequence. So we usually write it by this. So we denote it by xn. Okay, so recall the basic definition of convenience of a sequence. So we say that the sequence xn converges to a number L if given an epsilon positive. So you should think of this epsilon as an error. If given epsilon positive, there exists a natural number n, which depends probably on epsilon, usually depends on epsilon, n of epsilon, such that the modulus, so here I assume everyone is familiar with the properties of modulus, like triangle inequality, which is the most important one. So modulus of xn minus L is less than epsilon for n bigger than equal to capital L. Okay. So this is the meaning of a sequence converging to a real number L. And of course, so pictorially, what does this mean? So here is L on the real line. It means that you give me an epsilon. You think of this as error. You can give me any epsilon you like, and I will give you a large enough number n, so that if I draw this interval, this is L plus epsilon and L minus epsilon. Okay, so for large enough n, so from x capital N onwards, all of the sequence lies here in this interval. Okay, and that means that in particular there are only finitely many xi's which lie outside this interval. Maybe this is x1, maybe this is x10, whatever, but eventually all of the other ones, they lie in this L minus epsilon to L plus epsilon interval. Okay, so very often we see this the ordering goes wrong in this, that they say, some people write that if it is they don't write given an epsilon, they say there exists an epsilon. It's not that. You give me any error epsilon, I can find an n which has this property that afterwards, after this stage n, all the numbers are in this interval L minus epsilon to L plus epsilon. Okay. Yeah, so important in here is to think of the negation of this negation. What does it mean to say? What does it mean? Say xn does not, the sequence does not. Sorry, someone say something.
I think someone by mistake has unmuted. Yeah.
Okay. Yeah. So what is the negation of this statement? What does it mean to say that xn does not converge to this number L? Anyone?
I can find an epsilon.
Yeah.
Whatever n you are giving, I can find out some n bigger than that n, but that element not lies in that interval.
Yeah. Okay. So it means that. So what does it mean? That means there exists some epsilon naught, let's say positive, such that. So I will write in this, and okay, let me write also. It's just a rephrasing of what I think it was Kanakaraj. This means there exists epsilon naught positive, and okay, I didn't introduce subsequences yet. Maybe why don't we? Okay. Such that, okay, so maybe I'll just write it the same way. Such that for every n, there exists some number n bigger than n such that mod xn minus L is bigger than equal to epsilon. Okay, so it means that there is one epsilon naught which does not work for the previous statement. That means that whatever number you give me, I can always find some index which is higher than that, so that xn will lie outside of this interval. This is the L plus epsilon to L minus epsilon. Okay, so this is an important thing. So maybe it helps to just subsequences. Let's quickly define a subsequence. A subsequence of xn is simply a sequence, let's say xnj, where n1 less than n2 less than n3, so on. Okay, so it is again xn, a subsequence is simply members of the original sequence but picked in order, same order as here. Okay, so this n1, n2, n3 must be an increasing sequence in natural numbers. Okay, so so the same thing, whatever I've written here, in terms of subsequences, what you can say is that.
Hello.
In terms of subsequences, the previous negation can be written as follows. There exists epsilon naught positive and subsequence nj, or let's say subsequence xnj, such that xnj minus L is bigger than equal to epsilon naught for all j. Okay. Okay, is this fine so far? Yeah. Any questions? Okay, so yeah, in particular, these are usual facts. So maybe I will just take this for granted that you can prove this. So fact, or maybe before I do that, just let's talk about so definition. We say that a sequence xn converges if there is convergent sequence if there is an L such that xn converges to L. Okay, so here the notation, what I will write, this is common thing. So this, if xn converges to L, the notation will be this, xn goes to L. Okay, so xn is a convergent sequence if there is some real number that it converges to. So some basic facts is that if xn converges to L, then or let's say limits are unique. There is only one number that it can converge to, right? So okay. So you are aware of this, right? That you can prove this, that limit, if there is a sequence that converges, then it can have only one limit. Okay. Then what else? Then every if xn converges to L, then every subsequence xnj also converges to L. Okay, or let me write this properly. If xn goes to L, then for every subsequence xnj also converges to L. Okay. So how about algebra of limits? So algebra of limits, I will encompass all of this in one point. I'll just mention a few of them. That if you have one sequence going to say L1 and yn going to L2, then you can add the two sequences, and they form the addition of these two sequences forms a convergent sequence with limit L1 plus L2 and so on. And also you can do constant times xn goes to constant L1. All this under the same condition, that if xn is going to L1 and xn yn goes to L1 L2. So maybe in this fact, the first one, okay, so maybe I write maybe fact 0 in this is that convergent sequences are bounded. So yesterday we talked about bounded above and bounded below. If a set is both bounded above and bounded below, we say it is bounded. So convergent sequences are bounded, right? Because if all of them starting from some n lies in this L minus epsilon, L plus epsilon, outside of this there are only finitely many. So you can obviously encompass all of them in some big interval. So it is bounded. Okay, so just to do a few examples. Of course, the first one we study that it follows directly from this Archimedean property. So 1 by n goes to 0, right? Why is this? By the Archimedean property. So just to ensure that you see that the concept of limits heavily dependent on Archimedean property, which in turn depends on order completeness. So if epsilon is positive, modulus of 1 by n is 1 by n. So by Archimedean property, there exists a capital N such that 1 by n less than epsilon. But if n is bigger than or equal to capital N, the way that real number, the inequality works, 1 by n is less than or equal to 1 by capital N, which is less than epsilon. So modulus of 1 by n, which is 1 by n less than epsilon for n bigger than or equal to n. So the basic fact that 1 by n goes to 0 just follows from Archimedean property. Okay. So just to make sure that this epsilon definition that we can all work through it, let me just do very quickly one more, just a simple example. Let's see how to prove things just fully rigorously. Okay. So if you just take something like this, let's say maybe 2n squared plus 3 by maybe n squared minus 1. Okay. So let's say this is the sequence. So this is xn. What is the limit of xn? Anyone? As n goes to infinity, what is the limit?
It is 2, sir.
Can you hear me?
2, sir. 2.
2.
Will be 2.
Anyone? Can you hear me?
2, sir. Yes, sir.
Sir, 2.
Yeah, we can hear. I think they're answering it to be 2. Hello?
Okay. It will be 2. Someone has said in the chat. Can you hear me, Sushoban?
Yeah, I can hear.
I can hear you, but
I can hear you.
a lot of us said 2. Perhaps we're not audible to you.
Oh, yeah, maybe I didn't. I didn't get it for some reason. Okay, yeah. So 2 is the answer. Of course, you can either just think of this in calculus what you write, but just to make sure that rigorously we can all write this down, that with the epsilon definition. How does one do it? So you guess that. So guess is that xn goes to 2, but we have to prove this properly with this epsilon definition, right? So how does one do it? So you have to estimate what? You have to estimate xn minus 2. So if you give me an epsilon, I have to make sure xn minus 2 in modulus is less than epsilon for n large. So what is xn minus 2? It's 2n squared plus 3.
Sir, can you take n square plus 1? Because at 1, there is a problem. It's not defined at 1.
Yeah, okay. Yeah, it doesn't matter. We can take this. This is a sequence for n bigger than whatever. Yeah, or you take n square minus 1. It's okay. Yeah. So let's say we start with n equal to 2, right? Okay. So if n square minus 2n square plus 3 by n square minus 1, you have to look at the difference with 2 in modulus. How do we control this? So if you do this, the algebra, so if you take common denominators, you have minus 2n squared plus 2. So it has 5 by n squared minus 1, right? Okay, so the question is, if you give me an epsilon, can I make this, how do I make this less than epsilon, this quantity?
We have to connect somewhere that 1 by n something like, we have to some relation.
Yeah, how does, so maybe someone else can tell, how does one show? So for large enough n, how to choose large enough n so that this is less than epsilon?
In the opposite implied way, like 5 by n square minus 1 is less than epsilon is implied by n square minus 1 over 5 is greater than 1 by epsilon and so on.
Yeah, so you can do it several ways. So if you want, what we want is that, so that is now given an epsilon, we want a capital N such that 5 by n squared minus 1, let's say anyway we are dealing with n bigger than 2, n bigger than equal to 2, so it's all positive. We want this to be less than epsilon. So one way to do this is to solve this inequality. That is, we want n squared minus 1 is bigger than 5 by epsilon. That is n bigger than square root of 1 plus 5 by epsilon. Okay. So again, this is again the Archimedean property. Given any real number, there is always a natural number above it. Okay. So this is there. Okay. So in always, I mean, this, if you want, you can also show another way to show. Again, everything depends on Archimedean property. You can also show another way is that, say for n large enough, 5 by n squared minus 1 is also less than 1 by n. This is also true. Okay. So that's the way you prove certain things, this kind of things rigorously with epsilon. You just try to get an inequality. So that, now by Archimedean property, there exists a capital N such that n bigger than square root 1 plus 5 by epsilon. Hence, if little n is bigger than equal to capital N, we have 5 by n squared minus 1. Inequality goes the other way, n squared minus 1 less than epsilon. Okay. Because if little n is bigger than capital N, then little n squared minus 1 bigger than capital N squared minus 1 and blah, blah, blah. Okay. Okay. So maybe we can talk about some sequence which does not converge. So we have written here negation. What does it mean that, a sequence is said to be, if a sequence is not convergent, it's called divergent. Okay. So maybe we just write it down. If a sequence is not convergent, we say it is divergent. Okay. Okay, so just to give an example in this. So there are many examples, but maybe we can do, since we did 1 or 2 easy ones. So slightly harder one. Let's say if you take xn, maybe let's do cosine n pi by 8 or something like this. Does xn converge? What do you think?
Sir. No.
No. Yadaya, Mr. Yadaya is saying no. Yes. So why do you think so, Mr. Yadaya?
Because it's all oscillates in between -1 and +1.
Yeah, but can you make it rigorous? That's correct. It is, well, it is going close to 1 and -1, but how to make it rigorous?
By taking the value of n,
yeah,
n is equal to maybe it is multiples of pi by 8.
N is a multiple of pi by 8, but pi by 8 is not rational, it's not an integer. So what do you mean by taking n to be multiples of?
N to be, if we take sir n to be a multiple of 16, for example.
Yeah, so
and this will always be cos of twice.
Right, yeah. So what so we say here, so we one of the facts that we did here, I just stated it without proof, but I hope you could you can prove it, that if it is convergent, then every subsequence also converges to the same limit. Okay, so the point is, of course, we guess that it should not converge because cosine oscillates. So if you just play around, if you see that, so answer is no. Why? Because if you take n, for instance, you want to kill the 8 in the denominator first, so you take n to be a multiple of 8. Okay, but if you take n with 8 times, maybe just for instance, you take 2 power k. So all sort of 8 times powers of 2. So k equal to, so maybe we say nk, k equal to 1, 2, 3, and so on. What is the value of, what is x and k then?
That constant sequence 1.
Yeah, so it is cosine of 8 cancels, it is 2 power k pi. So all odd, I mean all even multiples of pi, these are all cosine of 2 pi, cosine 4 pi, and so on. All these are 1. Okay. But now, do you see what kind of subsequence you can take to get maybe -1?
All the odd powers, like
yeah. So if you take let's say mk,
1 plus 1 times 8, 1 plus 1 8.
Yeah, so you can take, for instance, some odd thing. So let's say 8 times 3 power k. So if you take this, then you will get that x and x mk. This is -1. So because here 8 will cancel, cosine of 3 power k is always odd. So right, all so then you get -1. Okay, so you have, what you have done is you have produced 2 subsequences with 2 different limits. So you can't have that the sequence converges. Is it okay? So this is one of the frequently common case. One proves that the sequence does not converge. Yeah. Hence we have found 2 subsequences which converge to 2 different limits. Hence original sequence xn cannot converge. Is it fine? Do you have some questions on this? So you should play around with these kind of things. So all you need to prove is that to show that some sequence does not converge is just produce two subsequences with 2 different limits. That's all. Okay. But okay, just to stretch this example, what about let's say yn? This is sine n pi by 8. What do you think about this? Does this converge?
This also doesn't converge.
This also doesn't converge. Okay. How will you try to show that? If you claim something, you should have some strategy to prove it. How should we prove that?
First take n to be multiples of 8.
Okay.
In that case, it will always be equal to 0.
Correct.
And we can take multiples of 4, which will include the previous values.
Multiples of
4, which are not multiples.
But all, see, in the sign,
multiples
sign
of
vanishes at all multiples of pi.
Multiples of 4, which are not multiples of 8.
Oh, but the point I'm saying, sine of n pi is always 0 for all n. Doesn't matter odd or even, right?
My idea is to keep the denominator equal to 2. I'm going
denominator equal to 2. Okay. Okay.
I'm going to choose a set of values for n.
Okay.
We should cancel out the 4 in the denominator, but we'll leave 2 there.
Okay. So what should that n?
I'm going to take multiples of 4, which are not multiples of 8.
Okay. Yeah. So we can take. So for instance, we can take y So choose nk. First one, you can do the similar one, 8 times whatever.
Sir.
Yeah.
Sir, n is equal to multiple of 8 multiplied by 4n minus 1, another is 4n plus 1.
Yeah. So I'm just writing down what this previous person just said. So first one, to produce a zero sequence, that is, okay. So if you take all multiples of 8, so maybe let's say, maybe just to take nk is 8 power k, then in this case, ynk is 0. But yeah, so then the other one, what you want to take? You want to take multiple of 4, let's say. So you want to take what? Just to write it down. You can take 4. 4 will give you pi by 2. Then what else you take? Which is not a multiple of 8.
Take multiples of 4, which are not multiples of 8. That's
Yeah. So
12 now.
Yeah. So 4, 12, and so on. So how do you write that for nk? Right?
This will be an AP, so we can write down the nth term.
Yeah. What is it?
It will be, we can compute the nth term. It will be a plus n minus.
So you want only odd multiples of
8 and minus 4.
Okay. So for instance, if you take this even even further, if you take 2k plus 1, for instance, then what will happen here? So if you take 4, 12, if you take 12, what will you get there? So for if n is 12, then 12 times 12 by 8, what is that?
We get an odd multiple.
It should be 2k minus 1, right?
2k
4,
plus 1
12, that is the sequence you want, 4, 12, and so on. So it should be 2k
for
minus
k starts from, maybe let's write 2k minus 1. Yeah. So if you write this, then you will alternate between what? So for first one, you will get sine pi by 2 when n is when k is 1, n is 4. So then you get this. Second one, you get sine of 12 by 8. So 3 pi by 2.
Minus.
Okay? That is minus 1. But okay. So you can, so you can change this to, so what else you want? The next one will again be pi by 2. What is it? So if you take the next one, so it's not 16, but 20. Yeah. Okay. So if you take 20 by 8 is how much? 5 pi by 2, which is again 1. Okay. So in this case, so even here you can choose furthermore. So you write it down properly. So if you do this alternates again, y and k alternates. Let me write it. It alternates between plus 1 and minus 1. Okay. So again, if you want, you have produced 3 subsequences, each with different limits. 1, 0, 1, plus 1. This plus 1 will correspond to 4, 20, and so on. The minus 1 will correspond. These all will correspond to plus 1. These guys will correspond to minus 1. Okay. And okay, just maybe this is quite easy, but just to say, sometimes other strategies will also help. But because we talked about algebra of limits, let me also indicate one way in that. So another way, these are all different ways to prove the same thing. Okay, sometimes some method may be more useful or less useful, so on. So another way, using algebra of limits, right? So what we did, so if this did converge, if sine of n pi by 8 did converge, so this sequence, maybe I write like this, then so there are trigonometric identities. Often there are algebraic things that one can use. So for instance, cosine of n pi by 4. Okay, this is 1 minus 2 times sine squared n pi by 8, right? Cosine of 2 theta, or what do you want to say? Cosine of what do I want to say? Cosine of 2 theta is what?
1 minus 2 sine square theta.
Yeah, cosine n pi by 16, right? Cosine of 2 times n pi by 8. So cosine of n pi by 4. This is 1 minus 2 times sine square n pi by 8. Yeah. Is that okay? Basic trigonometric identity, right? So if sine n pi by 8 did converge, then so does. So we did this algebra of limits. So if 2 sequences converge, then their product also converges. Then so does sine squared n pi by 8, right? Okay, but if sine squared n pi by 8 converges, then 2 times sine squared n pi by 8 also converges to some limit. So this will mean that hence cosine of n pi by 4 will converge. Is that clear to everyone? If we suppose that sine of n pi by 8 converges, by algebra of limit, the sequence of the squares sine squared n pi by 8 will also converge. And we have this algebraic identity between cosine and sine, cosine 2 theta and sine theta, which is this. So if sine squared n pi by 8 converges, this will converge. And this is a constant sequence 1 that also converges. So cosine of n pi by 4 will converge. But what's the difference? Cosine n pi by 4 and n pi by 8, what we did here, you do the same strategy. You take nk as 4 times 2 power k, maybe 4 times 3 power k. It's the same thing. So, but we know. So, but cosine n pi by 4 does not converge by an argument similar to the previous. Yeah, I probably spent more time than I should have in this, but doesn't matter. Okay. So just to give that several strategies are possible. That's okay. Do you have any questions on this? Okay. So the next one I want to talk about is.
I have a question.
Yes.
Will it be the case if we replace the sine and cos by any periodic function?
And that depends on the property of the the periodic function where you pick. Okay, so many times actually, so so if you take if you choose the sequence properly, then as long as it oscillates, then you will have a similar.
So by definition, the periodic function can be made to get to the same value again and again, right?
Yeah, that is true. But you also have to pick other values so that you will get two different subsequences. So for at least for cosine and sine, this you can always achieve that one of them is whatever. If you start with this, then So if it is a continuous periodic function and so on, then yes, you can always do this similar thing. Okay. All right. So the next one I want to do is let me just look at my notes. So probably I want to. What do I want to do? Yeah. So maybe I talk about monotone sequences. This is an important. Monotone increasing or monotone decreasing, either one. So just to recall definition, sequence xn is called an increasing sequence, called increasing, if xn less than equal to xn plus 1 for all. Okay, and similarly for decreasing. So for convergent ones, we have seen a few examples, but this one furnishes a wide class of the one that we will just talk about now. As long as sequence is bounded and increasing, then it is okay. Similarly for decreasing. So a basic theorem, which you have all no doubt seen, is that a bounded, let's say bounded above. Okay, so let me write this way. You can form the analogous statement for the other one. An increasing sequence xn that is bounded above is convergent. So this furnishes many examples. What is the quick proof of this? So if you have a increasing sequence, xn is increasing.
It is bounded above, therefore it has a supremum. Therefore, we are going to claim it is converges to that supremum.
Yeah, so let xn be increasing and bounded above. Let's say maybe by bounded above. Okay, doesn't matter. Anyway, bounded above. Therefore, by again, you see here we are using the order completeness. By order completeness, the set xn has a supremum. Let's say the supremum, we can call it alpha, and you know you want to claim that xn, the sequence xn, converges to alpha. Okay, why is this? We already know. So that means what? Again, just to recall this definition, we have to show that if you give an epsilon, there is an n large enough so that xn minus alpha less than epsilon. Okay, but so if xn, remember alpha is the supremum of this set xn. Okay, so we know that alpha in particular is the supremum, means it is an upper bound. You know, xn is less than equal to alpha for all n, because alpha is an upper bound. Remember, supremum is anyway always an upper bound. So in particular, if xn is less than equal to alpha, it is also less than alpha plus epsilon. Epsilon is positive, so it is always true. So you have to show the other inequality. So you have to show that all xn's lie to the right of alpha minus epsilon. Now, alpha minus epsilon is strictly less than alpha. So by property of supremum, there is some n such that x capital N is bigger than alpha minus epsilon, right? If you give me something smaller than the supremum, I can always find an element of the set which lies above it. But xn is supposed to be increasing sequence. So that means, but xn is bigger than equal to x capital N for n bigger than equal to n. So therefore, alpha minus epsilon is less than xn or n bigger than equal to. So if you look at stare at this one and this one, so maybe we call star and double star. This implies that mod xn minus alpha less than for n bigger than equal to. Okay, it's a standard proof. Okay, so another important property of monotone. So there is some, there are these concepts in combinatorics called Ramsey theory. That means that what a Ramsey theory says, even within high disorder, you can always find some pattern. The system has some, it may be chaotic, but even then you can still find some pattern. That is the point of this Ramsey theory. One of the theorems in this is this property. So theorem, so I may not, I don't know if there is some interest, I can prove it, but since I'm anyway running short of time, but anyway, so let's say any sequence, anyway, let's say we are always dealing now with real sequences without, so without further mention, we will always deal with real sequences. Any real sequence xn has a monotone subsequence. So that means it can either be monotone increasing or monotone decreasing. Okay. So you guys are familiar with this theorem?
Yes, sir.
Yes?
Yes, sir.
Okay. I mean, everyone or most of you, what is the situation?
No.
Sorry?
No.
No. Okay. Okay. So this is a nice theorem. So maybe we can prove it, and the proof is also, at least the proof that is commonly given. It's also very nice. It's a proof due to Polya. So yeah, perhaps let's do it. Okay. So after the proof, you should think about. So I will do the proof, but you should think about how can a sequence fail to have a monotone subsequence. So that is the key to this proof. So think about the way that a sequence can fail to have a monotone subsequence. That would suggest that how this proof, how to construct a proof. Okay. So this is a proof due to Polya, I suppose. So anyway, so let's do it. So let's say that a term, let the integer n naught, or maybe we call this, okay, so maybe, okay, so yeah, let n naught in n be, we say b, call n naught a peak if xn naught is bigger than xn for n bigger than n naught. Okay. So what does this mean? It means that we call n naught a peak if the sequence, the element xn naught is the largest one. After that, everything that comes is below xn naught. Okay. So if you draw a picture in, so if you make a graph, right? So that is, this is 1, 2, and so on. And x1 will be whatever value here. Maybe x2 is negative, maybe x3 here. So if it is a peak, so if 3 is a peak, then all sequences, all elements which come after it must be below. Okay. So this is a peak. Is it okay? The definition of a peak is that after this peak index, everything must be below it. Okay. So there are two cases. So we are going to deduce this existence of this monotone subsequence by two cases. Case 1, there are infinitely many peaks. Okay. So what happens if there are infinitely many peaks? So for instance, so maybe this circled point, and so 3 is a peak. So maybe, so let me just draw a few more. Okay, but if you see, so maybe this is 4, 5, and 6. But so for instance, okay, yeah, 4 is also, maybe okay. Let me just move this to be slightly bigger. Okay, so 4, 5. So 4 is not a peak because 6 is higher than 4, x6 is bigger than x4. But if you see the picture, assume it goes like this. So 6 is also a peak. So suppose like this, there are infinitely many peaks. Then what happens? So list them. So let's say the least peak is at n1, n2, and so on. Then what can we say about xn1, xn2, and so on?
It's monotonically decreasing sequence.
Yeah. So then, see, n1 is a peak. So all xi's consequent to xn1 lie below xn1. So in particular, xn2 is below xn1. But n2 is also a peak. That means n3 is bigger. So xn3 lies below xn2, and so on. Okay. So this gives a monotone decreasing sequence. Okay. So this is case 1, when there are infinitely many peaks. What happens if we have, so case 2, is the other one if suppose there are only finitely many peaks. So in this picture, so maybe if I change this picture, whatever I drew here, this was the graph of the discrete sequence xn. If I change this picture so that picture looks like this, that if there are only finitely many peaks, so after some stage, that means what? So let's say that is, so let's say n naught. Since there are only finitely many peaks, n naught be the last peak. So any finite number of natural numbers has a largest element, so that n naught be the last peak. So I understand, you understand last meaning the largest index of the peaks. Okay. Then we look at, let's say that n1 is n naught plus 1. Okay. Then let's say, then n1 is not a peak, right? Because n naught, there are a few peaks maybe. So maybe I just, let's say circle whatever, some index, whatever. I circled a few of them, whatever peaks are there, I circle. Okay, maybe this picture. Okay, but after this, there were no more peaks. So that means if you pick some index here, this is not a peak. What does it mean that it is not a peak? What can you say about those elements?
They are already monotone.
Well, not quite, right? I mean, what is not monotone? If n1 is not a peak, so let's go back and look at the definition of peak.
Then there should be some number which comes after it, but is greater than.
Yeah. So what is a peak index? Peak index means everything that follows it is below it. Okay. So if it is not a peak, that means that there is some element which comes after it, which lies above it. Okay. So since it's not a peak, therefore, oops. Sorry. Therefore, there exists an n2 bigger than n1 such that xn2 is bigger than xn1, right? This is the meaning of it's not a peak. There is someone after xn1 who lies above xn1. Okay, let's say that there is xn2. Now xn2, now n2 is also not a peak. Again, why is it not a peak? We have chosen n naught. N naught is the last of the peaks. So in this picture, this is n naught. After this, there are no more peaks. So n2 is somewhere, n2 is here, n2 is bigger. This is n1, n2 is bigger. So n2 is also not a peak. Therefore, there exists n3 such that n3 bigger than n2, such that xn3 is bigger than xn2. So you proceed in this way. Inductively to get xn1 a sequence. So maybe let me just add a page to get a subsequence xnk such that xn1 less than xn2 blah blah blah. So this is a monotone. Or let's say, okay, so I should be careful here, even though it's a small point, it's a, you have to put greater than equal to and so on. So if it is a peak, then it is strictly above. If it is not a peak, then it can be equal also. That's okay. So just to be careful here. So xn3 bigger than equal to xn2 and so on. So I should just put this kind of stuff. Okay. So this gives a monotone increasing subsequence. So there are only two cases. These are mutually exclusive, that either there are infinitely many peaks or there are only finitely many peaks. Either way, you have found a monotone sequence, subsequence. Okay. Do you have any questions? This is a standard proof. It is not.
Sir, I have a question.
Yes.
Not regarding this. When you started discussing this, you talked about the Ramsey theory. Could you spend a couple of minutes on that?
I mean, okay, that would take me away from real analysis, which is the subject matter of this series of lectures. Yeah, I mean, okay, so you can forget. Okay, I just wanted to sort of. Sorry.
I just want to know if there is any kind of relevance. Why you spoke about it? There must be something about this.
No. So that's what I said. This okay. You should just forget about this. But what I wanted to tell was, so Xn is any sequence, right? So sequence can behave in any way you want. So you should think of what I said. Ramsey is that Ramsey theory means that the sequence can behave very wildly. That is okay. But within this wild occurrence, within this wild system, there is some orderness. That is some pattern. What is this structure within this chaotic thing? The structure is that there is either a increasing subsequence or a decreasing subsequence. That's what I mean. Okay. So this is the crudely what Ramsey theory says. It is prevalent. You can find this in graph theory and other things. But I won't go into those things. Okay. Yeah, it is not really important for this. I just mentioned it because this is one instance of this Ramsey theorem. But anyway, forget about it. Any other questions?
Yeah, sir. That means we can decompose a sequence into monotone subsequences.
Monotone subsequences. I mean, decompose means what?
Decompose means the union of all the subsequences will give me the entire sequence, and the union should be the disjoint union.
Well, okay. I mean, what sense do you mean? So the remaining ones you.
Yeah, remaining ones you apply this process again and get another subsequence.
Okay, but again,
monotone.
Yeah. So okay.
Provided, of course, provided you have infinitely many terms.
Yeah, but again, a sequence for us is always an infinite sequence. We don't well at least.
No. I mean, after you take out the first monotone subsequence, the remaining terms, if we assume that the remaining there are remaining infinitely many terms,
okay,
so that is again a subsequence of the original sequence. So on that you apply this process again.
Yeah.
So you extract another monotone subsequence,
right.
And so in this way you can do. Now my question is is it true for every sequence we'll get a finite number of this monotone subsequences?
No, so that is probably not true, and you should think about how to construct a counter example to this. Okay, so yeah, so of course if you start with either an increasing subsequence and so on, that is just one, but you should try to construct a counter example to this what you said, that maybe if you decompose like that, then it's not, you don't stop at a finite stage, you can do it forever.
Okay, sir. Okay, thank you.
Yeah. So anyway, so we have okay. So yeah. So maybe now I do quickly. So I wanted to sort of indicate certain equivalences to all these several important theorems that we usually learn. But let me just state one of them. This famous Bolzano-Weierstrass. There are several proofs I will see. So just like yesterday, I didn't want to, like yesterday I went quite a bit over, but so let me, yeah, Shushoban, can you just remind me when I have 5 minutes left? Is it already?
I think we have 2 minutes.
Okay, fine. Then I will stop with Bolzano-Weierstrass. It's anyway, this one, it's quick, this one. Okay. So what is the Bolzano-Weierstrass? It's a theorem. It says that okay, so every bounded sequence has a convergent subsequence. So stated in words, this is the Bolzano-Weierstrass theorem. And as I mentioned, there are several proofs. I mean, one of the ways you can prove this is by the nested interval theorem. But since we just proved this, maybe let me give because I only have 2 minutes anyway, so let me give the quick proof of this. So let Xn be a bounded sequence. Okay, then by the theorem that we just proved, Xn has a monotone subsequence. Let's say Xnj. Okay. So this is a previous theorem that we give. Either it's monotone increasing or monotone decreasing, whichever one of them. So then, but this sequence is bounded. But Xnj is still bounded. If a sequence is bounded, then any subsequence is also bounded, right? But now this is a monotone sequence. So we have just seen first one of the theorems that we proved is that in this previous one, if the sequence is increasing and bounded above, it is convergent. Similarly, if a sequence is decreasing and bounded below, it is convergent. But if the sequence is bounded, it is both convergent, bounded above and bounded below. So either way, you're covered. Xnj may be decreasing or Xnj may be increasing. But either way, it is bounded above and below. So in either case, you can hence. But since Xnj is monotonic, so it has a limit. Let's say that is this subsequence Xnj converges to some L. Okay. So you see that Bolzano-Weierstrass follows immediately from this monotone stuff. Okay. So just to recap, maybe I will just spend 5 minutes of next lecture trying to do this. So we have this order completeness. So I will finish now, Sushoban. Yeah. So we have order completeness. We showed that order completeness implies the nested interval property. This we did yesterday. Okay. And if you see the proof clearly today, so this monotone convergence, I will call this monotone convergence. We use order completeness for this, that we showed that increasing sequences is convergent, bounded and bounded increasing sequence is convergent. We use order completeness. So from there you can go to monotone convergence. Then we have Bolzano-Weierstrass. So I will just call it Bolzano-Weierstrass. So from monotone convergence, we could prove that Bolzano-Weierstrass. So any bounded sequence, we extracted this. Okay. And one can, next time I will maybe just indicate. So one can also prove the Bolzano-Weierstrass from the nested interval. Using nested interval, you can prove Bolzano-Weierstrass. This is also quite commonly done. It's another way to do it. So in some sense, and you see that actually you can also go the other way. It's not very hard to show that if you know Bolzano-Weierstrass, then you can also prove nested interval. So I will, whatever I have done, I will draw in black, remaining I will draw in red. This is also true. Okay. And in fact, from there, from nested interval, you can even go back to this. Okay. So in many ways, many of these things are equivalent. Okay. So you see that we started with order completeness, which is sometimes called axiom of completeness, and we derived several things here. But my point is many of these things are equivalent. Okay. So it's a good exercise to try to see, because each one gives a different flavor to the proof. So it's a good thing if you know several of these equivalences. Maybe next class I will indicate a few things, but I will more or less, I didn't even do Cauchy sequence today. So I will probably have to do that. Okay. Yeah. So anyway, yeah. Any final questions?
There is a question in the chat box. If two subsequences of a sequence converge to the same limit, then does it imply the given sequence is always convergent?
Okay, but only for 2 subsequences. But if you change that, that is not necessarily true. Okay, so but then there is a theorem that if you take a sequence, okay, if every subsequence has a further subsequence that converges, then the whole sequence converges. So, but if only 2 subsequences converge, then it may not. Then that does not imply that the whole sequence converges. Okay, you need to impose some other extra condition. So next time we will probably see that if you have a Cauchy sequence, then only one convergent sequence, that is enough, subsequence. So if xn is Cauchy, if you have a subsequence that converges, then the whole sequence converges. But that is only for Cauchy sequences. In general, this is not true. Okay. Yeah.
I have a question, sir.
Yes.
If you take 2 subsequences of a sequence such that every term of the original sequence belongs to exactly one of the 2 subsequences.
Yeah, so I mean, okay, there are many kinds of questions like this. Okay, I encourage some of you to, I mean, you should think of these kind of counter examples and examples. This is good for you. Okay, but yeah, maybe since time is up and I don't want to, yeah, you should think of this. Maybe some of these things I will put in the problem set for tomorrow, but there are many questions. Okay, so I just I don't want to give the answer or try everything, but you should try to solve some of these things and maybe talk it over with some of your colleagues attending this workshop and so on. Okay, so I will probably yeah, let's not do all of this. Okay, so yeah. Okay, so anything else?
Sure. Are there any more questions?
Yeah, I mean, okay. I hope you don't misunderstand. Just try. If you have a question, you first try it yourself in this, because these are this is very good for learning these concepts. One of the best ways is construct examples and counter examples yourself. Okay? So if not, maybe towards the end of the lecture series, we can collect some questions and give some solutions. We'll see. Yeah. Okay.
Okay, so I think we should stop for today then, and we will meet again tomorrow. So tomorrow is the tutorial session, and I think the tutorial sheets will be circulated, I think, at least by tomorrow morning. So you are requested to please go through it and try those problems and before the tutorial session. Yeah, and I have also circulated a Google form with for the attendance. I hope everyone has marked it. If not, please, I am sending it again in the chat box. Please do mark your attendance. Yeah, I think we can close for today then. Yeah.
Okay. Yeah. Thanks. Bye.
Thank you, Kosuhik. Yeah. Bye. Bye, everyone. Good night.